Hey guys, this is Professor Janacek. I want to talk about parametric equations. You'll recall that equations have the form y equal to something in terms of x, or perhaps x is equal to something in terms of y. One or the other gives us an equation. Of course, in this case, these are written as functions, which makes them nice to work with, and we kind of like that. But parametric equations have the form x is equal to something in terms of some other variable like t, and y is also written in terms of something in terms of that variable t. So we have both x and y written as functions of a new thing, t. That new thing, that new variable, t, is called a parameter. Hence the name parametric equations. I have a set of equations written in terms of some other variable, t. Let's try some examples. Let's take a look at x is equal to t squared plus t and y is equal to 2t minus 1. There's our parametric equations. And let's graph those. Recall from graphing, you may have often done a table of values. That's exactly what I want to do here, but rather than a table of both x and y values, I want a table of t, x, and y values. All right, so let's see, we can try, something simple. Let's start with 0 for t. Notice all I'm going to do is evaluate my two equations here for that t value and see what we get for x and y. In this case, if t is 0, then x is also 0 and y is -1. Not so bad. Let's try 1 for t. If t is 1, then x is 2 and y is 1. 1 works. Let's try -1. Put in -1 in for t. We get a -1. We get a 0 for x and a -3 for y. All right, not so bad. Let's see if we can do the same thing with the 2's. Let's try a 2 for t. That gives us 6 for x and 3 for y. -2 for t gives us 2 for x and -5 for y. Now I want to use one more point. Let's try a -1/2 for t. Now if you don't see why I'm choosing this now, don't worry, I'll show you once we get to the graph what gave me the idea to use this t value. If we have -1/2 for t, that gives us -1/4 for x and -2 for y. Now all we need to do is plot our points. We're going to plot them in terms of x's and y's. Notice my graph has only x's and y's, doesn't have a t, so I simply need to plot the x, y values. All right, take your time when doing this. Our first ordered pair is 0, -1. Make sure you get that in the right spot. Graphing is so simple, but sometimes we get in such a hurry that we end up putting things in the wrong spot and it looks funny. 2, 1, 0, -3, 6, +3, 2, -5. Now, if you didn't think to use the -1/2 in the graph, let's pause for a moment and see this graph is already starting to take some sort of shape. In fact, it's looking kind of like a parabola on its side. The only thing I don't really know is how far over does this go? Is it going to kind of bubble? Is it going to come out a bit? Or is it going to stay low like I've written it? We really don't know. So that's when I thought, well, let's put another t value in there. I do notice that it looks like I might need something out here. I just don't know where exactly that's going to be. So I kind of worked backwards. looking at that y value of -2, and that showed me which t value to use. So that's how I came up with that last point, -1/2 for t, which gives me -1/4 for x and -2 for y. Of course, you could add a few more points if you wanted. There's definitely going to be some point down here that out at the x value of +6, some other y value. I'll let you guys do that one if you'd like. But there we go. The graph looks sort of like a parabola on its side. Now, what's the beautiful thing about parametric equations, you'll notice this is not a function. It does not pass the vertical line test, so it cannot be a function. However, each of these equations, x and y, those are both written as functions. So I could actually consider this as two separate functions stuck together that make something that wasn't originally a function. So that's the beauty of them. I can take something that's not a function and write it as a collection of functions. Moving on, let's see if we can do a little calculus with this. Let's find dy dt. Well, remember that both x and y are functions of t, meaning dy dx is really dy dt over dx dt. And since dy dt, well, actually, let me go ahead and jot these down. Since y is equal to 2t minus 1, then dy dt is just 2. And since x is equal to t squared plus t, then dx dt is 2t plus 1. So that gives us dy dx is 2 over 2t plus 1. Not so bad, pretty simple. Just make sure you're always looking at this in terms of the t parameter first, find those independently, and then put them together in your final answer. Don't get ahead of yourself. Common mistake to get ahead of yourself on this one. All right, now let's see if we can eliminate the parameter for these. So we have x is t squared plus t and y is 2t minus 1. Let's start with the y value. I think that's going to be a little easier to work with initially because it's linear. It doesn't have that exponent of 2. Since y is equal to 2t minus 1, then we can isolate our parameter, and that's exactly what we want to do first. Then t is, what is that, y plus 1 over 2, right? And now, if we take our other function, x, which is t squared plus t, then we can simply replace the t's with the y value, with something in terms of y. So x is y plus 1 over 2 quantity squared plus y plus 1 over 2, right? Again, all I'm doing here is replacing those t values with what we've come up with in that first statement. All right, I think we can simplify this a little bit. X is y plus 1 squared. Remember, you're going to write that as a binomial and multiply it out. That's y squared plus 2y plus 1 over 2 squared is 4, plus, I do recognize that I have a denominator of 4 here, I have a denominator of 2 there. Let me go ahead and get the common denominator on those, and that would give me 2y plus 2 over 4. Then we can combine those. We get x is equal to y squared plus 4y plus 3 over 4. Ta-da! There we go. No more t's. The parameter is gone. It has been eliminated. We have x now as a function in terms of y. Hope this all makes sense. Enjoy!